showed some alertness on the students' part, and maybe makes even more clear the power of hashing. Remember when I told you how Google eliminates, make sure that they don't get multiple copies of Skiena's book by getting a hash code for the book and testing any document that hashed to that code had to be Skiena's book, and they didn't even have to look at the file? Well, somebody said, wait a second. A couple people said, wait a second. You're saying the hash code is 256 bits long. That means that if you want to store a bit vector, let's say, of 0, 1 for all the documents that are in there, okay, you've got to have 2 to the 256 bits in order to make sure that every possible hash code can be in your table. How many people see what I'm saying? How many people are confused about what I'm saying? More people. Okay, remember, what did we do? Last time we had this idea that there was a copy of a file on the web, like Skiena's book, and we hashed it to compute a key, an identifier that was basically 256 bits. And later, if Google crawls another book, another web page, they're going to hash that. If that number is the same as this number, that means that this file is one they have already seen. Does everybody see that? They don't even have to look at this file because the space of possible hash codes is so large, and the set of documents which would correspond to ones in this bit vector are so sparse. 1 out of every zillion things will be a real document, and the rest of them are going to be codes that have never been seen, right? So someone said, people noticed, wait a second, we can't store a bit vector this big, even if we are Google. So how can Google keep track of what documents are uniquely on the web? The answer is they take these codes and they hash them. They build a hash table of hash codes. Okay? Think about that now. Now they've got a universe of, if Google has 100 million documents, 100 million 256-bit keys. They want a data structure that will let them search that quickly, right? Is this particular key there or not, right? If it's not there, insert it again. So what can they do? They can come up with another hash function, let's call it h prime, that takes one of these 256-bit keys and hashes it to a smaller key, and then builds an honest-to-God hash table on the hashed keys. Does everybody kind of get that idea? A hash table should be size proportional to the number of elements that are in it. For Google, that would be 100 million or so, how many documents there are, right? Now it's got an array the size of however many buckets Google wants, okay? And they're going to store links. And now when they want to know, someone has a pirated copy of Skiena's book. They hash it. They go to the appropriate bucket. They walk down the list until they see an exact match of the hash code. And then they throw it out. Okay? And this is now a perfectly compact and reasonable Google-sizable data structure. Yes?
So we're saying Google is hashing phrases on pages which are then being stuck?
No. Google, remember, what did we say that the idea of recognizing document similarity? Forget about sub-document similarity. Let's think back to the big picture.
Not thinking like sub-phrases and pages.
Not sub-phrases. We're looking at phrasing. In this case, we're looking at identifying duplicates of files. Okay? Each file is represented by its hash code. We now have a library of perhaps 100 million hash codes that have been seen on the web, right? Now, how can we represent that data structure? Well, why not build a hash table on those hash codes? And now the hash table is of modest size. You can access it quickly, and it does exactly what we needed to do. Any questions about that? Yeah?
How long did you say the hash table was?
Okay, so now let's think about the world. Let's say Google has 100 million documents. Okay, that sounds like a reasonable guess to me. You know, you have to ask Google. Okay? But what I'm going to do for each one of these, I am going to hash them to a unique to a 256-bit key, right? Meaning it's a hash function like that, sum up all the bits, but the modulus is 2 to the 256. So I've got 256 bits of information that I'm using as the record for that document, right? Now, I could have represented that set of hash codes by a bit vector, a string of 2 to the 256 bits, where the ith bit is going to be 1 if that particular document was there. That would be an incredibly sparse bit vector, because 2 to the 256, does anybody know what 2 to the 256 is, base 10? It's big, but what is it? I mean, people, that's why one reason you invent calculators, but yeah, ballpark.
It's 2 to the 10 to the 25th, right? It's 10 to the 3rd to the 25th, like 10 to the 75th.
This is about 10 to the 75th. That I can believe. Okay? What is 100 million? Does 100 million sound like a large number? Depends upon who you're talking about. That's 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 to the 9. Does everybody see that there's an ungodly difference here? This bit vector is impossible in the universe we live in, okay, whether or not it's owned by Google. But if we now build a hash table on 100 million things, that is a Google-sizable problem. You may not want to do that on your laptop, but that's not what Google is doing, right? And does everybody see that by building a hash table on those hash codes, okay, now you've got a reasonable data structure for storing the unique representative of every file on the web, okay? Any questions about that? Yes?
If you're going to be double hashing, does that suggest you should just do a single hashing smaller instead or not?
The way we're doing it is the way I'm doing it here. So let's not, there's different, double hashing means different things than I think what you're saying. Okay, so what we're doing here is we're using hashing twice here in two different ways. One is to take a big file and construct a unique representative, such that nothing else in the universe that isn't that file is likely to have that hash code. The second thing we're going to do is build a data structure on these hash codes. And that data structure is logically going to be a hash table. Okay? Any other questions here? Okay, yes?
This more likely reduces the chance of collisions, right?
What?
You're going to have a higher chance of collisions.
I will have a high chance of collisions in this table. But this I'm going to treat like a normal, real, honest-to-God hash table. Is there a problem with collisions in a hash table? That two keys in a, let's say you have a hash table of 1,000 items. Let's say two hash codes collide on that. Is that a problem? No, that's why we have linked lists, right? And that if there was a collision of hash codes, you search the linked lists. And the way you resolve the collisions was, assuming that the collisions lists are reasonably short, then you can walk through it and it's still efficient, right? So what we're going to do is we're going to use the first hash code on the document to construct an almost certainly unique representative of all files on the web. The idea that any file on the web had a collision is extremely small. Okay? Then when we hash it into a real hash table, yeah, there's going to be collisions. But these collisions are typically going to manifest themselves as relatively short lists. And so how do we look up if Skiena's book is on? I have a new pirated copy of Skiena's book. How do I find it? I hash that thing. I go to the appropriate bucket. I walk down the list. Is this hash code exactly equal to Skiena's hash code? No. 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 End of list. This is a new book. Okay? Any questions? Okay? Any questions about this? So learning to think about hashing is a very important thing in the world. It's an important thing on Google interview questions. It's an important thing on managing big things. It's not as important in here as I'd like it to be, because we're going to be talking more about worst case analysis. And so usually we're going to be thinking in terms of binary search trees and things like that. But you should know in your back of your pocket that hashing is a great thing and how it is useful. Any questions? Okay. Any questions? Okay. So now I'm definitely going to seal this up. But okay. So what I'd like to now do is to get to the problem of the day, which, if I understand correct, we'll leave it like that. Okay. The problem of the day, which has to look like this. You were given as input two n numbers. You want to design an algorithm to partition the numbers into pairs with the property that we minimize the maximum sum of the pairs. Okay? So suppose we're given the numbers 1, 3, 5, and 7. There are 3 possible ways to partition it into 2 pairs. One's got to have a buddy. Once you fix that buddy, the other 2 have to be paired together. So if we look at these things, the sum of each pair, this is 4 and 14, 12 and 6, and 10 and 5 and 8. We want it to be the case that the biggest partition is as small as possible. So this would be the one that we want. Okay? Any questions? Why might we want to do this? Can anybody think of a reason why I might want to do this? Okay? Yes. Balanced trees, I don't see where the tree comes in. But why would I want to do this as an application of something? Okay? I don't see it. I'm looking for another face, just for any other faces here? Yes?
You might want to load balance the server so if you have several incoming streams of web traffic, you might want to pick and you have like a smaller number of, say, applications.
Okay, you're thinking something about load balancing servers, and maybe there's probably a way to state these things. What I think about is balancing teams. Let's say that I had a class and I wanted to be fair in assigning homework partners in here. Let's imagine I had an algorithms class and every student had an algorithms ability, okay? And I wanted to pair them up as teams. What would be the advantage of pairing them up so to maximize the sum of minimum algorithm ability? What does that mean, yeah? I make the teams basically as fair as possible. Does everybody see that? If I paired the 2 lousiest students in the class, they would have no chance against the 2 best students in the class, right? But this way I'm ensuring every team maximizes their minimum competency. Does everybody get that idea? So how can we do this pairing? Okay? Let's say a new face. Let's say yes, you. So you're telling me that what I should do is take, if the skills, probably you're saying first, okay, you're saying pair with highest to lowest ability, which probably means first you're saying sort by ability. Is that what you're saying? So you're saying sort these people by ability. Let's say 11, this guy's a 13. Let's say make 4 more. This guy's a 14. This guy's a 23. He's on the ball, 24. What do I got? I need 2 more, right? Let's say 27 and 32. And then what are you going to do?
Well, if it's already sorted, then you can just pair 5 with 32 with 7.
So you're going to pair them up like this. Does everybody agree? That's what he wants to do. And how did I end up with odd number of numbers? Okay, you didn't see 15, I guess. Okay. Done. Does everybody see this? That's what we're going to do, right? Okay? Does everybody get the idea of the algorithm? Now, is the algorithm correct? Okay, remember we at one point had this idea that there were proofs of correctness needed to convince me of an algorithm. I agree with you, you have an algorithm that given numbers produces pairs. Can you convince me that this in fact minimizes maximizes the minimum pair over all possibilities? Okay? Yeah.
Well, I mean, I guess we could start with, maybe do it inductively. So we start with, if you have the smallest number, the way to maximize it would be with the largest number. Then you have a smaller list, and the way to maximize the minimum there would be the same way.
Okay, maybe. You're saying inductively. Okay, one question here. As a rule, when you do it, just to think about, so there's something to think about here. Which one of the pairs is going to be the smallest? The one have the smallest sum. Yeah? You say it's always going to be, wait, no, the smallest two would be these two. That much we agree. But now you've got n over 2 pairs. Is there one of these positions that always has the smallest sum among them? No, is right, okay? Some people might say, oh, these guys are going to have the smallest sum. It's not necessarily that the inner two need to have the smallest sum, right? It could be that these two guys are, that all of these guys are zeros, and all of these guys are slightly better than this guy, right? And then this might be the biggest sum, okay? Or it could be that this guy's, this guy's a superstar, and no matter how dumb this guy is, that would be the biggest sum. Does everybody agree with that? So we can't look at this and say one of these pairs is best. I mean, at least by position without looking at the numbers. Does everybody agree? Sometimes you've made these things without looking at the numbers, once you've sorted it, right? Okay. Can anyone come up with an argument, let's say, that's convincing that this has to be the best possible ordering? Okay, let's try you. Okay, I am not sure I'm hearing that. Okay, and so that may be my fault. Let's try another one with a louder voice.
Anything added to the maximum number will be the maximum sum. So if you add the lowest number to the maximum number, that will be the minimal maximum sum.
Okay, that I don't believe is true, because again, I think it's kind of the same argument that I had just sort of gone. If I may be misunderstanding you, so don't take it personally. But it is not true that this is going to be the biggest pair, or that's going to be the biggest pair, okay? And how do we do? Okay, what's your idea?
So you first work on the assumption that the largest number must be paired somehow with some other number.
Yes, okay.
So the largest number in this case, 32,
Oh,
must be
sorry.
paired with something.
Yeah.
And so if you select any number other than the smallest number, then you will find something, then there exists something else which is even smaller, so you're not minimizing. So if I selected any other number,
Okay, so you're trying to say if I don't select this thing up with this thing, if I don't pair this guy up with this one, if I pair him up with this one, okay, then that pair is going to be bigger than it needs to be, or something like that. But that doesn't convince me. Which is the biggest pair here? Okay? In fact, let's think about it again. Suppose my numbers were 0, 0, 0, I guess 10, 10, 11, 11, 11, 11. You're saying, gee, if I don't pair this guy up in here, something bad's going to happen, right? If I pair this guy with that, that can't possibly be the right solution. Is that true? No, because the bottleneck is over here. Does everybody agree with that? This is going to be your biggest couple. And how you marry these guys to those guys doesn't really affect it. Okay? How many people see why that argument didn't work? Okay, I'm trying to show you that there's some level of subtlety here that one has to kind of think about. Okay? Let's try one more, and then I'll do my way idea. Yeah.
For example, if in the middle of that there is the largest sum, and you have to, if you chose, say if the range was by index 3 and 5, and the largest index is 9, then if you chose any index to pair with that lower number above that index 5, it's going to make that largest sum even larger.
Okay, this is, I think, the kernel of an idea I like, okay? And let me just try to say it my way, and let's see if we understand this, okay? Computer scientists know two ways to prove things. How do they know how to prove things? By induction or by contradiction, okay? I don't think it's induction here, because you can't peel the outer layer off and do something automatically. So how do you prove it? You have to prove it by contradiction. That's not quite a proof, but that's almost a proof, okay? Now, what is the idea of the contradiction proof? Suppose we have a bunch of numbers here that we, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's make it 12. 5, 6. Okay. Suppose, let's say, that this algorithm did not work right. Okay? This did not always minimize the sum of the maximum, minimize the maximum sum of a pair. Okay? Then if it doesn't work, what does that mean? Somewhere there is a set of input numbers, and these happen to be them, that this algorithm does the wrong thing on. Okay? What does that mean? Okay? That means that I paired them up like this. And my maximum pair was, let's say, this one. Okay? And you're saying, ha, you got it wrong. Okay? There is a better way to do it. And I'm going to say, oh, which is the maximum pair? Okay, in your solution. Okay? And you're going to tell me, well, it's going to include this one. And this one is going, let's actually, okay, that's funny. Now let's try to think what the consequences of this thing are. Okay? Suppose it was a different one. You're telling me that this one is going to be paired up with this one. Well, let's think what the contradiction is. It's funny. I try not to think about these before I come to class to be fresh, and now maybe I'm stuck here. But let's try to see what the contradiction is. If you had to have paired, let's take a look at the bigger number here. Okay, this was the biggest pairing that I got. Does everybody agree with that? And you're telling me, no, in your pairing, okay, then this one had to be paired, this biggest number here had to be paired with somebody. Who could it have been paired with if you managed to get a smaller, bigger pair? Yeah?
One or two.
It has to be paired with one of these guys. Does everybody see that? If I got a pair sum of this and this is my biggest one, and you claim to beat me, well, this guy has to be paired up with someone, right? And the only ones that could do better than me would be if you paired it up with either one or two. And that's fine, right? But then look at this guy. This guy is bigger than this one. For you to get a smaller pair, who did you have to pair it up with? Either one or two. Does everybody see that? This guy also, if he's going to have a smaller sum than this thing, he has to be paired up with one or two, right? And what about the last one, the third one here? Who does he have to be paired up with? Either one or two, or else, the sum of it is going to be bigger than my previous sum. So what's the problem? The problem here is I have three guys under those conditions who have to be paired with two guys that are smaller than it. And that's not possible because each guy can only be paired up with one. Does everybody see that? That is the source of the problem. You told me I was wrong. Okay? I showed that if you claim to have a bad example, that is impossible. Okay? And that is the argument why this is right. How many people understand my reasoning here? Okay? And so this is the way a proof probably should look like. Is it what is your strategy here? My idea is contradiction. What are my assumptions and why? Yes?
Well, wouldn't you have always the possibility that the two closest to the middle would have a value greater than the largest and the smallest?
Okay, what is the situation here? I paired them up like this, in this nested thing. You told me I'm wrong. What does me being wrong mean? Now, on my example, I can look at it, and there was a particular pair, which when I look at those numbers, that were the biggest of my pairs, right? If you're telling me I'm wrong, my algorithm is wrong, you must have a way to do it such that the biggest pair is smaller. That's what it means for my algorithm to be wrong, right? So, okay, in your biggest thing, I don't know which your biggest pair is, but I know you had to put this guy with somebody. I know you couldn't have put him with this, and I know you couldn't have put him with anybody bigger. So you had to put him with someone smaller. And again, you've got, if this was the kth inner loop, you've got k things as big as my biggest pair or not, and k minus 1 possible things that you can mate it with. So you can't do it. Yeah?
You could sort it in a different way that would make it less possibility that the middle two would be higher than the others. For example, you get the middle of the array, and you put the smallest one at the beginning, and the second smallest after the middle.
This is not about really about, this is conceptual, it's not really about sorting the array so much as it's just about realizing sum. The bottleneck, the score of the algorithm is what was the biggest sum that you had, the biggest sum, you know, the biggest, the biggest sum, okay, that you realized. That was done by a pair. If I sort the items, there's still a pair of items. My pair of items would be k up and k down, because that's how I constructed them. If you have an algorithm that does it differently, that's up to you. But this guy's going to have to be paired with someone. This guy's going to have to be paired. This guy's going to have to be paired in something. And the sum of these pairs are all going to have to be less than or equal to this one. And there isn't a way to do it. Okay? Any questions about that? That's the kind of reasoning that we would like to do about correctness. Okay? Any questions? Okay? So it should show us, this is a good problem, it shows us something about proofs of correctness, and it shows us something else, the power of sorting. How fast does this algorithm run to pair them up? N log n after sorting. If it was already sorted, how fast would my pairing algorithm be? Order n, right? So sorting encapsulates, you know, the bottleneck in a lot of these kind of operations. Okay, any questions? Yes?
Well, since it's restricted to only like integers, if you use something faster than n log n, like very quick.
Okay, so there are some, okay, so the question of whether you can do faster than this kind of sorting that we're doing, there's, the world of sorting is an interesting and complicated thing. And if you assume special properties of the keys to be sorted, okay, like they are very small numbers or something like this, sometimes you can do better. But here we're going to, until let's say maybe the last class of the sorting unit, we're going to be assuming that the only operations we're doing is comparing pairs of numbers. Because it's not really only sorting numbers, you want to sort names, right? You want to sort things. And the general thing that you want to do is to compare given two strings, which one is ahead of it in sorted order. So for algorithms that work that way, n log n is going to be the right answer. And I'll hopefully convince you more of that later in, in a couple of classes. Any questions about that? Okay, good. Okay, so why do CS professors like talking about sorting? You know, there are several reasons, but the two that are, let's say, most salient to me are, one, it is the best studied algorithmic problem in the universe. There are a zillion interesting sorting algorithms, okay? If you're bored and you want something wonderful to read a book by an author named Knuth, Volume 2, called Sorting and Searching. Okay, this is one of the greatest books ever written, and it's a book about sorting algorithms, okay? And the amazing different sorting algorithms and the analyses of these things. So this, you know, so you can really get excited about this if you're a computer scientist. But the other reason why we're going to do it, that's more important, is that kind of the principles of many algorithm design things, like randomized algorithms, like lower bounds. He was asking me, oh, can you sort better if there's something weird? We'll talk about lower bounds later. We'll talk about randomized algorithms. We're going to talk today, next class, about divide and conquer, okay? These ideas are important ideas for all kinds of algorithms. And so sorting makes a good laboratory to think about it, okay? Any questions? Okay. And again, the thing that I want to talk about, just to make sure you understand this, if there were not sorting, if sorting took n squared time, the world would be a different place, okay? Again, you could kind of imagine a Twilight Zone episode where somebody woke up and suddenly there was no n log n sorting algorithm, okay? And what would it be like in this world, okay? Would there be phone books? There would not be telephone books in this world. Why? Because if you took the Manhattan phone directory with 1 million names on it, if you sort it with an n-squared algorithm, the number of steps is too long. Civilization could not produce telephone books if you had nothing better than an n-squared sorting algorithm. Okay? N log n sorting algorithms, this is only 13 million steps. This is 250, this is million, billion, trillion, okay, steps, okay? So there is a tremendous difference between n squared and n log n. And sorting is typically the key to the difference between an n squared algorithm and an n log n algorithm. Any questions about that? Okay, so we are fortunate that the creator gave us n log n sorting algorithm. Okay, what other things are important to know about sorting? One thing that's true is that's again, as an algorithms person, I like to know about different sorting algorithms because there are ideas, and I like to learn about those ideas. But from a street level algorithm design thing, you know, the way you work, okay, often what you need to know is how to recognize when something is an application of sorting. There's a tremendous number of algorithms that are basically of the form sort and do something. This algorithm was sort and do something, okay? And inventing an n log n sorting algorithm may have been hard, okay? But once you know that it exists, you can solve a lot of problems using that. So what good is sorting? The classic application of sorting is so that you can do binary search. It should be clear that if you have a sorted list, if you look in the middle of it, if the key that you want is above the median key, the key has to exist in the second half of the list, or the array, as opposed to the first half. If you start out with n items, after one comparison against the median element, you can throw out half the array. How many times can you have to throw the array away until you end up with only one element? How many? Log n. Okay, so that's binary search. That's important. But there are lots of other applications of sorting that you sort of have to realize to see it. Suppose I am given a bunch of numbers, and I want to find out which pair are closest to each other. Okay? So how would I figure it out? You guys all have GPAs. Which pair of you are most identical in GPA? How would I figure this out? Okay, how would I do it? Yeah?
You could sort of do, if they're sort of just do the bubble without actually swapping anything.
Okay, no, we don't talk like that. What we talk like with these things is sort it. And once it's sorted, what do we know about the two students? First of all, what are we sorting it by? Suppose I want to find which students here have the most identical GPA. I want to sort you guys by what? GPA, not by name, but by GPA. Does everybody see that? And then the two people who are closest to each other are going to be sitting next to each other in sorted order. Why do I know that? Why do I know that the two people who have the closest GPA of any pair in the class, why do I know that there isn't somebody between them? You're saying if it's not sorted order, well, if I sorted them, they would be, it might be that there's two guys between the one, but, yeah?
If there exists someone between the two, then that means that your closest pair has to be the
Does everybody see that if Joe and Jethro here, they couldn't be the closest pair by GPA if when we sort them, Natasha's between them. Does everybody agree that either Joe and Natasha are closer, or the closest pair is either Joe and Natasha or Natasha and whatever the other name I use for it. Right? Does everybody see that? So sort them, and then once you sort them, a linear scan finishes the job. Okay? Any questions? So finding the closest pair is sorting plus a linear sweep. What about element uniqueness? Given a class of n items, are they given an array of n items? Are they all different, or are there duplicates? How can I tell if there are duplicates in a set of n things? Okay, yeah. Sort them by whatever the key is, and
the closest to each other are the ones that are
If they are identical, they would be closest to, they would be neighbors. Does everybody agree with that? So you know after you sort them, the duplicates are all going to be next to each other. And you can make a nice sweep and eliminate all duplicates, right? So using this is basically sort and do in linear time. Any question? The mode, question, yeah.
For that previous example, could you also use a hash table?
Could I use a hash table to identify duplicates? And the answer should be yes. And in fact, that's exactly what Google was doing up here, right? They were trying to identify the duplicates copies. So certainly you could use, to identify duplicates, you could use hashing. Now, in the worst case, what's going to happen? If you get very unlucky or use a terrible hash table, everybody, no, if you got very unlucky with your hash code, all the hash codes will go to the same bucket. Does everybody agree with that? And so in the worst case, you've got, after you've hashed everything into your hash table, they might all be in a linked list of size n and you've done nothing. So the worst case, that isn't good. But in practice, that's a great thing to do, right? In practice, we would expect that the n items we put in will be in different buckets generally. Each list is going to be of constant size. We'll be able to go through the list and see if it's unique. If not, insert it. If so, throw it out. Okay? So in practice, a hash table is a good thing for that. In the worst case, you might get in trouble. Okay? But in practice, a hash table is a great thing for that. Any question? Yeah?
As a follow-up, so like practically, would you use the hash table for efficiency, or would you use the other method for consistency?
Okay, would I use the hash? Would I use a hash table, or would I use the sorting thing? Generally speaking, okay, I would probably use the hash table in practice. Okay, in an algorithm design problem where I need to worry about a worst case bound, which is a very useful way to be able to think, I would know never to think about a hash table. You give me a hash table when I ask for a worst case bound, you're going to get a worst case result on that problem, right? Okay? But in practice, hash tables usually should be very good things. You know, one can quibble about it exactly. So if it was a huge amount of data, it turns out there's some reasons why sorting and sweeping might be better. But in general, generally speaking, hash tables are good things, and in the real world, people will be happy with you for using hash tables. Any questions? Okay, good. What if we wanted to find the mode? The mode of a set of items is the one that occurs most frequently. How do we find the mode, okay, of a set of items? Okay? How do you find the mean of a set of items? You know this statistical mean, mode, median stuff. How do you find the mean of a set of items? Okay? The average of a set of numbers, yeah? How do you do it? Yeah?
You add them all and then divide by the number.
So what's the complexity of finding the average, the mean? O of n. How do you find the mode? Okay, the most frequent number that occurs. Okay? How would we do it? Okay? How could we figure out the most frequent item in an array? Yeah? Sort it. And does everybody see that after we sort it, all the duplicates are next to each other, right? So now after I sorted it, my items are going to be in blocks. Does everybody see this? And these are all identical. These are all identical. How would I go about finding what the mode is? I'll start from the beginning and count. Are you the same? Are you the same? Are you the same? No, you're not the same. Okay, the first block had that many items. Now go through and continue on from here. I'm going to scan each item once, so it's going to be order n, but I will then find where the, find which is the biggest block, and that biggest block will be the mode. How many people see what I did here? This should be clear. Anybody not see what I did here? Okay? Any questions about that? Yes?
Theoretically, if you knew you had a bunch of duplicates, could you do something with like pigeonholing and cut it in half and see if you have your max and your min?
Okay, if I knew I had duplicates, could I do something better than sorting and things like this?
Well, after it's sorted, instead of doing another ON sweep.
Well, okay, if after sorting it I do an ON sweep, to me an ON sweep is about the cheapest thing I can do on my array, right? So if I've spent n log n for sorting, n log n plus O of n sweep is what? N log n, right? So the cost of the sweep is already something like nothing to me, okay? So I'm not really trying to get it down, okay? And, in the worst case, I'm going to have to sweep through all those items to figure it out, okay? Any questions? There's any questions about that, okay? Good. The other statistic of interest is to find the median. What is the median element of a set of n numbers? Yeah? It's the one that has the same number of elements above it as below it. So how do we find the median? What is the easiest way to find the median? Yeah? Sort it and then look in the n over second position in the array. Does everybody agree with that? So this gives you an n log n algorithm to find the median. In fact, there is a very clever way to do it that is linear time, that you wouldn't stumble across, that's clever, okay? Now, in general, so there is a faster way to do it, but basically it turns out the way to do it involves sorting, but not completely sorting, okay? So sorting is still kind of the real idea behind this thing. Any questions about it? Okay, good. And let me just show you one more application of sorting that shows you that there are more high-powered. These things should have all been pretty easy. You should be able to understand those algorithms pretty trivially. Let me show you a more powerful algorithm problem that is ultimately really solved by sorting. And this has to do with finding something called the convex hull, which is kind of the shortest, simplest description of a set of points you can make. So you see you've got a bunch of points in the plane. Think of them as nails sticking out of a board, heads of nails sticking out of a board. If I stretched a rubber band over the whole thing and let go, what's going to happen? Ka-chung! It's going to go and form a shape. Does everybody see that? It's going to form a polygon that includes all the points. Okay? That is what we call the convex hull. Okay? And so you can imagine the following problem of, given as input a set of points, construct this hull, construct this polygon, okay, that contains all the points. Okay? And this turns out to be the first thing you want to do in almost any geometric problem. Okay? So how can we find the convex hull of a set of points efficiently? Okay? Rhetorically, it was meant, but yes.
Get the point which is at the middle, and then try to find the points that are...
You're saying try to find a point in the middle and then look at the ones that are outside of it, and, don't know exactly. There's different things that you're saying that might mean. Okay? Let me show you the simplest idea that I know how to do this, that makes the sorting idea kind of clear. Suppose we sort the points by their x-coordinate. Actually, at the risk, is there a way of listing this? This may be a bad idea. Let's try something. Let's do an experiment. Is this going to work? Probably not, but let's see. Okay. Okay, stop. Let's look at this thing here. Suppose we sorted these points by x-coordinate. I'm going to now insert the points from left to right based on the x-coordinate. What's going to be happening here? First, I insert that point. Then I insert this point. Then I insert this point. Does everybody see I've got a triangle, and that's a convex thing, right? The next point I insert, is this going to be inside or outside the polygon? Why does it have to be outside the polygon? Because I sorted them by x. It's always to the right of the polygon. Does everybody see that? And so now I know that this point has to be outside the polygon. Okay? And here you need a little bit of geometry, but it turns out that what's going to happen is, if you take a look at the last point you inserted, it might cause that to no longer be needed, right? So you might have to delete these things. But I'll claim that there's a way to do that efficiently. Okay? But what's kind of neat is because I sorted these points from left to right, I know that I never need to test whether a point is inside the polygon. Does everybody see that? By definition, as I build it, it's always outside the polygon. And it's going to be either a neighbor of the last point we inserted, or it's going to eliminate the last name. It's going to cause the last point to be enclosed. So there's a way to fix up the polygon quickly once the thing is sorted. And in fact, finding this convex hull turns out to be linear time once you have sorted the points. It's an n log n problem, but once you sort them by the x-coordinate, everything else from then is linear. Any questions about that? So there are a lot of grown-up algorithms that use sorting as its sort of underlying idea here. Any questions? Well, that's capturing the hard thing about this problem. Any questions? Okay, good. Okay, so when it comes to sorting, I would like to give you there's a little bit of programming grown-upness that I want you to make sure you have, okay? It should be the case that in practice, in the real world, you never program your own sorting algorithm. You are beyond the point of programming your own sorting algorithm, okay? Why? Because any reasonable programming language should have a library that will contain a sorting algorithm in it. Does everybody see that? So from a point of view of using sorting algorithms, anybody who says, oh, I had to sort this data, I wrote quick, wrong thing to do. The right thing is to say, I called a library, okay? And the interesting thing about sorting is that you could abstract a lot of the details of what you mean by sorting to something called a comparison function. When you first talk about saying sort the data, someone's going to say, do you mean from biggest to smallest or smallest to biggest? Okay? That's not an algorithmic question difference. That kind of thing should be encoded in. Implicitly, when you want to sort it, there is some kind of a notion of what you mean by a collating sequence of what things do you want before what other things. So when you're sorting things, do you want Skiena, capital Skiena, to be before or after lowercase Skiena? Okay? If you use different versions of Unix and you do ls, they sort the files in different ways. I don't know if anyone's ever experienced that. That's because they use slightly different comparison functions to do this thing. But basically, when you have a sorting job, you should not be writing quicksort. You should not be writing Heapsort. You should be thinking, what is the order I really want these strings to be in? And then write a function whose job it is to take any two elements and decide which goes before the other in sorted order. It's the equivalent of a less than operation, right? And basically deciding whether little Skiena is bigger than big, goes before big Skiena, is big Skiena less than or equal to little Skiena? Any questions? Okay? So when you're doing these things, you should be using a library function. Again, you use different programming languages than I do. I'm an old C man. Okay? But what does my sorting algorithm take as its arguments? It takes as input the array to be sorted. I learn how big is, how many elements are there in my array. To sort the first n items. Each item is a certain number of bytes. We're assuming if it's an array of regular things, right? And what I need to specify is a function. I provide a pointer to a function that given two items will report true or false depending upon whether the first one is before or after the second one. Any questions? So any sorting job in real life, you call a library function and you make sure that your comparison function does what you want for your specific customized job. Any questions about that? Okay. Any questions about the pragmatics? Okay. One last slide, just for something to think about when I'm not here, when you're not here. You know, one other thing is you sometimes have to think about what you do with equal keys, okay? Sometimes you're sorting records. And often if, let's say, we're sorting people by, when you're sorting people in a telephone book, you sort according to the last name, but then if there's ties, you break the ties on the first name. Does everybody realize that? So often in many applications, you have secondary keys, which you will blow up. And the way you implement these things, this is done in the comparison function, right? Your comparison function would be to compare two names. Are the last names equal? If so, look at the first names. Does everybody agree with that? Okay. So, something to file away if you're curious. Somebody who knows about quicksort, think about it. I don't want to talk about it now, because we'll talk about quicksort next class. But think about what happens if you quicksort something that consists of n items, all of which are 5. Okay? Right, and you'll find that sometimes some algorithms do strange things when you do that. And so sometimes you have to program your algorithm a little bit carefully to make sure you handle equal elements right. Any questions? Okay, that's not what I really wanted to talk about now. Okay, so now you should know why sorting is important. You should know how to apply it to algorithm problems. You should know how to deal with it if you have a programming job that needs sorting. Now let's look at some of these sorting algorithms because they will tell us something about algorithm design. And I'd like to spend the rest of class talking about a special sorting algorithm, a special class of sorting algorithms revolving around selection. So presumably you have all seen this algorithm selection sort, which works by scanning through the array and repeatedly pulling out the smallest element in the array. Does everybody kind of get that idea? So we have for n items, let's say we have a group of items in an array. Okay, and we have the items are 1, 7, 3, 2, 6, 5. Let's put a 5 at the beginning. We find which is the smallest item, and we put that first, right? And the smallest one first, maybe we'll reverse those two. Now we try to find what the second item is. I guess I should do it like this, right? This is now 1, this is now 5. I look for the smallest remaining item. This would be 2. I swap it, that's 2, and that's 5. I find the smallest remaining item, that's 3. Put it there. Find the smallest remaining item, it happens to be 5, right? Find the smallest remaining items, it happens to be 6. 7's got moving around a lot, right? And now I have the items sorted. That's selection sort. Any questions about that? What is the time complexity of selection sort? Yeah? N squared? The answer is it depends. Okay? And let's take a look at this. What I do claim is it should be obvious that this is a loop that goes around n times, and we have to find the smallest item and then pull it out of the array and put it first. Does everybody agree with that? Those are the two steps. The running time should be the time, n times the time it takes to find the smallest plus pull it out and put it first. Okay? And you were telling me, well, that's got to be n squared, because if I'm scanning through an array, it takes n steps to find the smallest, and over 1 steps to actually swap it and move it up, right? So n times n plus 1 is n squared. Does everybody agree? But the interesting thing is if we use a better data structure than an unsorted array to hold these items, we can actually do better. Okay? Suppose we used a balanced binary search tree that supported insert and find the minimum in logarithmic time. Does everybody remember that? If we had a balanced binary search tree where we have the keys, we first load everything up into a balanced binary search tree. How do we insert another item? Well, we would insert it to the bottom and then use the rotation magic, but it would take log n time to insert an item. How much time does it take to find the smallest in our current array? In a tree. How much in a balanced binary search tree on n items? How do we find the smallest item? Log n. How do we do it? We go bop, bop, bop along the left pointers until we hit it, right? This guy is the smallest item, right? We can put that guy first in the array by finding the min and then delete it, right? How much time would it take to delete it? You say O of 1? Well, it's O of 1 to get rid of that pointer, but if it's a balanced binary search tree, you may have to rebalance, right? And so the magic of, the only guarantee I gave you about balanced binary search trees is deletes would take log n time, right? So if we did a balanced binary search tree, finding the minimum took log n time, deleting the minimum took log n time, n times log n plus log n is n log n. Does everybody see that? So using a better data structure made this selection sort idea run in n log n time. Is there any questions about that? This is why data structures, powerful data structures like dictionaries based on balanced binary search trees are so powerful. Okay? Any questions about that? So do people see that selection sort can be done in n log n time using a balanced binary search tree? Any questions? Okay. There is another data structure. Oh, okay. There is another simpler data structure than a balanced binary search tree that is worth knowing about. And it's an instance of an abstract data type we will call a priority queue. What is a priority queue? A priority queue is basically a data structure that is going to allow you to do 3 different things. Okay? It's going to allow you to do an insert. You can insert a new key into the priority queue. It's going to allow you to find the minimum. Or instead, if you don't want to find minimums, you can instead say, I want to only be able to find maximums. That's really the same problem, right? But finding one of them. Okay? And deleting the minimum or the maximum. Okay? So again, either you're going to be either going to have a min heap priority queue, in which case you're doing these, or a maximum priority queue, in which case you're doing these. We're not going to assume you're going to do both. Any questions? Okay? So the thing that should be clear is that these 3 operations can easily be done using a balanced binary search tree in n log n time, just like I did then. Insert an item, it's just tree insertion, log n. Find the minimum, bop, bop, bop. It's the height of the tree, log n. Delete the minimum. I find the minimum. Once I have it, I delete it. That's 2 log n operations, meaning log n. Any questions? What's important to know about priority queues, it's important to learn to think in terms of priority queues. Yes, this is a special case basically of what a dictionary is. But the basic idea of a priority queue is something that comes up over and over in algorithm design. And when I'm talking to a student about an algorithm design, they said, yeah, well, maybe if I stick it in a list and I do something, that person doesn't sound like an algorithms person. When they say, oh, I build a priority queue, and then they're now thinking in terms of these abstract operations that priority queues do. It's often that a lot of the algorithm problems we think about are going to be in terms of these operations. And so this should be an abstract type that you have in your head, okay, to call out for designing things. Yeah?
Could you just please explain it again? Why is it different from deleting from the normal balance tree? Because it still takes long for deleting.
So the question is, the way to think about it is a dictionary. You saying, how is this different from a tree? Okay, a balanced binary search tree. And the way I think about it is, balanced binary search tree is an implementation of a type, right? A heap is an implementation of a data type. The abstract type is given by its operations. Does everybody agree? Now, a dictionary is a big, complicated thing supporting 6 different operations. Okay? So complicated, I didn't even tell you how to rebalance trees in here, right? A priority queue is a data structure that has a simpler set of operations. And this metaphor of using a priority queue occurs often enough that learning to recognize it and talk about it in terms of saying, oh yeah, use a priority queue, okay, is an important kind of realization to have. Any questions? Okay? So let's think a little bit about when priority queues come in handy. Okay? And one thing that I remember, again, there was a time in my life when I was single, and I had to date. Okay? And, you know, there were a roster of possible people I could have dated. Okay? And I had to figure out, who do I ask out for Saturday night? Right? What is the data structure that I should use to do this? Okay, is it a dictionary on people's names? The answer is, it is a priority queue. Who is it that I want to date on Saturday night? The person I think is most desirable. Does everybody agree with that? So I want a data structure that is ordered by desirability. Does everybody see that? And so what should my week operation be? Okay? Thursday night, look at the priority queue. Find what the maximum value is, right? Call this person. Hopefully, they will agree to a date, and I will then reevaluate this person. Does everybody agree? I will, if my opinion of them changes, okay, either up or down, what am I going to do? I am going to delete them from the priority queue and then insert them again with the new score. Does everybody get that idea? And next Thursday night, what am I going to do? Okay, I am going to go and say, who is at the top of my priority queue? Does everybody see this? And if people's evaluations go down, they are not going to, they're going to be lower priority to be called. Any questions about that? So the key here is not their name. That's auxiliary information, as is their phone number, I hope. Okay? Any questions about that? Does everybody kind of see that? Yes? Did it work? Well, I'm married now, so I guess did it work? So in the long run, I guess the answer is yes. Okay? Good. Any questions? Just kind of see what it means, because this is now, again, I'm not organizing my data structure on names. I'm organizing it based on priority, on ranks, on a numerical field, and I am constantly interested in the best that is there, but the best that's there is changing. I call somebody up, they say, forget you, I'm never going to talk to you again. I either don't reinsert them, or they go in with a much lower priority. Does everybody see that? Okay, good. Okay? Again, there's a lot of simulations and a lot of situations where the same metaphor occurs, okay? Where items are coming in. Sometimes you have all the items at once, in which case you can sort them, and now you know them in order from best to worst, right? But in the course of the dating situation, maybe I meet somebody, okay? It's a dynamic thing. There's going to be changes to this. That's why you need a data structure for it, okay? And the situation where you want to figure out what's the biggest thing I know about so far in a world where there are insertions and deletions, this is what a priority queue is. Any questions? Okay, good. Any questions about a priority queue? So it's important that you learn to think in terms of using the word priority queue for this kind of metaphor. That's kind of important that you have that in your head. We're now going to talk about a specific implementation of a priority queue, which is interesting and cute, but recognize we already showed that you can do a lot of this stuff basically with a balanced binary search tree. But heaps are a good implementation of a priority queue that's kind of particularly slick and cute, and I do want to talk about it, okay? But the important thing is to learn to think about why priority queues are important. Any questions? Okay, good. What is a heap? How many people have seen heaps before? How many have not seen heaps before? Okay, most of you it looks like. A heap is a binary tree, but not a binary search tree, where the keys are labeled with the following properties. First of all, it's going to be as balanced as God can do. Okay, all the leaves are on at most 2 levels, and all the leaves are shoved as far over to the left as possible, so that this is as balanced as you can possibly do with n keys. But the important thing is that the ordering of the keys is not search order, but it has the property that the root key is going to be greater than all of the children. And that's true for every node in the tree. It's going to be bigger than all of its children. These conditions describe the shape of the heap. This describes the ordering of the heap. Any questions? So here is an example of a heap on years, okay? And what you can see is this is a perfectly balanced tree. I inserted the items, bop, 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 bop. There's no wasted space at all, right? It's as balanced as you can have it. We also have, this is a min heap. So if we look at it, the number on the root is the smallest of all of these numbers. This number is smaller than everything below it. This number is smaller than everything below it. This number is smaller than everything below it. Okay? Is this number necessarily smaller than this number? Not necessarily. Okay? So we're not, but we are know that every item is smaller than everything in its heap below it. Okay? That is the heap order on a tree, the heap labeling power. Any questions? What makes this good? Where is the smallest element in the heap? The root. What else makes this good?
Log n.
There's a log n smell in this thing because it's as balanced as it can. So the height of this thing is going to be a log n size data structure, which means that if you can do something that does constant work per level, it's going to be a log n operation, cost per operation. Does everybody see that? Okay, so that is what a heap is. Let's see. Let's watch a movie quickly. The Heapsort movie, just to make sure that we understand what this is doing. I haven't tried to do this before. Am I on? Am I getting the Heapsort movie? No, let's try the Heapsort movie. Uh-oh, if I can't get this... oh, wait, there it is, there it is. Oh, that's why. Okay, so let's see. Actually, let's come back here for a second. Sorry about this. Okay, let me try one more time. Let's get Heapsort the movie. Bang. Go to it. Okay, and now I think my problem is I've got... Oh, here it is. Good, right? This is Heapsort the movie. Now, what are we doing? We're inserting these items. How do we build the heap? We start inserting it from... We put it in the next cell in heap order. And then readjust the heap if it's happy. This is a 1, right? That's fine. It's happy because it's less than its root. This is a max heap. Here's an 8. Is it happy? Not happy. To make it happy, it swaps with its parent. And it's now, this guy's now happy, and that guy's happy, but not the root. Here's a 7. We insert that in there. Is it happy? No. We move it up. Now, this element is less than the guy before it. Its parent, which is good. And this is less than its parent. Okay, so that's how you build a heap. Any questions about that? Okay, now let's start trying to sort this thing. Okay, now they're going to show you in the Heapsort movie how the order of these elements, we store them in an array. There's a very cute thing going on. If we look at this thing, this is the 1, 2, second element in its heap. Its children are going to be stored in the 2 times 2 and 2 times 2 plus 1. Element I in the heap, its children will be in position element 2i and 2i plus 1. So there's a way to store this heap very compactly in an array. Does everybody see that? Okay. Now what is this doing? This is doing heap sort by repeatedly finding the maximum element, and then deleting it, and then readjusting the heap. So how is this readjustment going on? The biggest one now is 6. How are we going to get rid of it? We're going to put 6 at the bottom, put what was there up at the root. This guy can now be deleted, but we have to readjust the heap in order to do it, right? So in other words, if we have the element we delete from the bottom was the bottom rightmost element, there's no problem, okay? But the biggest one has 2 children. We've got to readjust it as a heap. So the claim is we swap the min, the max with the last element in the heap, then readjust the heap in order to keep it balanced, okay? And that's what this thing is doing. Any questions about that? Yeah?
So if this is O n log n and constant space, why do we ever do merge sort?
Okay, so why do we do different sorting algorithms? As a first order of approximation is to learn and the beauty of sorting. So as a first approximation in here, any n log n sorting algorithm is as good as any other n log n sorting algorithm. There are differences, but I don't want to make too much of that. The main reason is there are different ideas that are going on. Any questions? Okay, so this is the movie. You can watch the movie when you wish. Okay, let me try to see if there's a way to file. What does it mean? How do I review this? Full screen, is that it? Good. No. Trouble. Okay. Boom, put that down. Put this here. Good. Okay. So let me just talk to you about how heaps work quickly. I've shown you the movie. Let's now understand the basic points here. We're going to want to store things in heap order. That array property held because there was this very cool property that if we have a perfectly balanced heap tree, okay, we can represent a heap on of height log n by an array of n elements without any pointers. That was kind of the cool thing. The pointers in a heap are kind of implicit. If you take a look at this one, what is the parent of 1963? Okay, it is going to be, well, it's in the 7th spot. Divide 7 by 2, that's 3. My claim is this is the parent of 1963. Does everybody see that because of this nice, neat ordering, we can actually represent this conceptual tree by just an array without pointers? That's kind of slick. Okay, any questions? How do we readjust the heap? Okay, we agree that the way we built it in the video was what? Okay, we started with an empty heap, then inserted the item. First we started, the first item was 5, the next item was 3. We insert it in the right position. Here I'm going to have the biggest element at the root. If I insert a new item, if this item is bigger than the root, if what I had before it was a heap, if I swap these two, note that it stays a heap. Why? This item is now happy because it's less than its parent. This guy is going to be happy because it was less than its parent before, and now the parent has gotten bigger. Does everybody see it? So after a swap, it's perfectly happy. The only one that might not be happy is Grandpa. Okay? Because Grandpa might now be less than its child, right? So we can keep swapping up. How much time does it take to decide if I'm bigger than my parent? How much time does it take to decide if I'm bigger than my parent? O of 1. I do a swap, it's O of 1. I can get up there in a total of time proportional to the height of the heap, which is log n. Any questions about that? So building a heap, how much time should it take to build a heap? Okay? How much time should it take to build a heap by this insertion algorithm where I insert it and then insert in the next open spot in the array and trickle it up? How much time should that take? Yeah? What? Log n per insertion. How many insertions am I working on? N. So it's n times log n to build a heap that way, right? And that's a perfectly fine thing to, since I'm trying to sort in n log n time, right? How am I going to readjust the heap after I delete somebody? Okay. Let's say that this was the item 17. This is, let's call it 6, 3, what am I going to say? 10, 12, 10, 8, and 5 and 2. Suppose I want to delete the last item, this guy, because he's the biggest. The way I'm going to delete it is to delete the root. I'm going to take the item that is in the last rightmost leaf here, which was 8, and put that guy there. Now the shape of my heap is right. I've deleted the maximum. The only problem is I don't have a heap order necessarily. How do I decide where the biggest element is? Okay, you see what I did? I put what was a leaf now in the roll as the biggest guy overall. Is it going to be the biggest guy overall? No, because if not, it wouldn't have been a leaf, right? So it's got to slide down to the right position. How do I decide which element is the biggest overall? Well, it's the second biggest that was there, which had to be either here or here. And in fact, this seems to be the biggest one. Does everybody agree? And so I can now put 10 up there and element 8 here. Do I now have a heap? Maybe or maybe not. I got to compare it to my children. If either of my children are bigger than me, the bigger the children takes that and I take their spot. How many people see what this procedure is doing? Okay, any questions? What is the time that it takes? Okay, the time it takes is log n to patch up a heap after I put in a middle element here. Any questions about that? So what is the running time of Heapsort? My claim it is n log n. I'm going to build it in order n time. I'm going to delete these things. Okay, the root n times, that's going to each take log n. That is an n log n algorithm for dealing with heaps. Any questions about that? Yes?
Are we ever going to care about space complexity or not?
Are we ever going to care about space complexity? In general, we're interested in space. In general, for worst case analysis, we care about big O space complexity. So we would say a balanced binary search tree uses order n space. The heap uses order n space. By one measure, that's about the same, right? That's the same. On the other hand, we can also keep an eye out and say, practically, wait a second. A heap is great. There's no pointers. There's no, a balanced binary search tree, half the stuff is pointers. Okay? So in fact, heaps are very space efficient. Okay? Because we don't have to, and that's a kind of a nice thing to have. Okay? Recognize the difference between what's in practice and what's in big O. We will, if there's a tension, we care about big O here. Okay? But once we understand everything, we're not immune to the idea of saving half the space if we can do it. Any other questions about heaps? Yes?
Would it differ for the root to be the greatest in one of those under is lower, or would it be better if the root was the lowest?
Okay, so the question is, do you want the root to be the smallest element, or do you want the root to be the biggest element? And the answer is, on some sense, it depends by application. If I'm trying to maintain my dating desirability book, do I want on the top of a heap to be the most desirable person or the least desirable person? Okay, most desirable, right? So now do I score them in terms of points of value or in terms of deficit? How many points off I take for them? That would decide whether it's a min or max heap, okay? But the algorithm is the same. Notice it's just like the sorting thing, where the difference is a comparison function. Any questions about that? Okay, anything questions about anything else here? Okay, if not, is it time? I guess people are getting restless. Okay, take care, and I'll see you guys on Tuesday. Now, hand in your assignments electronically. Okay, has anybody ever succeeded in doing that, by the way? Okay, hand it in electronically, and let's hope it works. Okay, thank you.
What I meant by, like,